Once you've had a look at some of the more introductory notebooks to understand how the harmonized data access works, and maybe had a look at some of the introductory Sentinel-3 notebooks to understand what that data contains and how we can work with it, you may want to have a look at some of the case studies and applied examples that we've got to share with you in this training. So if you navigate back into the Ocean folder, you can then go into Ocean Case Studies, and you'll see there's various examples here that you can have a look at. There's two examples here using two sets of different products from the Copernicus Marine Service catalogue, so you can have a look at those. These are working with model data, so you actually get, as well as the surface view that you get from a satellite, you've got a depth dimension as well that you can look at, and there's various different parameters that are derived from these models around the biology, chemistry and physics of the ocean, so you can have a look at those. We've also got two examples here using Sentinel-3 data. The first one here, the Cyanobacteria example, which is the one I'll show you in a minute, uses ALTRI data at level 1, which is the same data that we looked at during the HDA example in an earlier video. And then there's a second example here which looks at marine heat waves, and this uses both data from Sentinel-3 from the SLSTR instrument to look at sea surface temperature, and then also a longer term archive of sea surface temperature which you can get from the Copernicus Marine Service. For this video I'm just going to demonstrate a bit about the Cyanobacteria example. This follows on nicely if you've looked at the previous video on working with ALTRI data, because we saw that the Baltic Sea is an optically complex area where we often have problems with traditional algorithms, and this notebook will give you a bit of more of an understanding as to why and what's going on in this very interesting ocean area. So this notebook starts like all of them, which giving you a brief overview about what the point of the notebook is, what you can expect to learn, the different tools that we're using. And in this case, we tell you a little bit as well about what cyanobacteria blooms are and how Copernicus data can be used to observe them. In brief, cyanobacteria are a type of algae. They photosynthesize and they live all across the world's oceans, but they can actually be a bit problematic when they occur in large congregations and large aggregations where they bloom, as we call it, in coastal or fresh waters, and are linked to various different health impacts in humans. So it's really important for us to be able to monitor these to understand and manage coastal water quality, for example. Copernicus data is great for identifying and looking at these blooms because we can pick up the color of them, and that's why we're using ocean color data in this example. But we can also use other data to support our understanding. So we can look at temperature, we can look at ocean physics in general in terms of currents and levels of stratification to understand why blooms are happening where they are at certain times. So the first thing we do, as with all the notebooks, is import the libraries that we need, and that's what happens in this section here. The following section, as with all the others, is about getting the data that we need. So in this case, we're looking at the Sentinel-3 ALTRI level 1 data again, as we did for the HDA access notebook that you may have watched the video for. To access the data that we need for this particular case study, you'll need to put your username and password in here to generate the access keys and tokens, etc. necessary to work with the API. We've provided a JSON file here for you. You'll see them in the JSON templates folder over here if you want to look at them in more detail. And this bit of code basically will execute the query for the particular data that we need here. After that, we're setting up a few parameters for the images that we want to create. If you read all the narrative around these, it'll explain them a bit more. You can also read the comments that are within the different code boxes. It will tell you what each different line of Python is doing. So once we've done this kind of initial bit of setup here, we can run our query, which is what this section does. And you can see earlier, here's where the query was submitted, found the results were then shown here. And we submitted the request to download this data to our local thing, and you can see here that that completed. It was this file, and it's stored in the products folder over here, and it's about 675 megabytes worth of data, and it took 14 seconds to download. As before with Sentinel-3 data, we have to unzip it in order to use it, so that's what this part of the code does here. And then we start opening up the data set. Because Sentinel-3 data is quite large and we're working in quite a limited environment in Jupyter Lab, there's lots of people using this, so we have to use a certain amount of memory each. we've designed this bit of code in order to maximize the opportunity you have to work with this data, to subset the images and reduce the resolution with which we plot. This doesn't actually affect the image quality ultimately too much, but it allows us much more flexibility in how we manage the data. So that's what this section is doing here. Here we then open the different files that are within the .cdf folder from the Sentinel-3 data for level 1. We open the different bands because actually what we want to do in the rest of this notebook is create what we might call a true color image. So this is as close as you get to, say, a photograph from the ULTI sensor. So we're looking at red, green and blue channels that come from the instrument, and we're going to create what we call an RGB or a true color image to show what's going on in the water. So here's where we extract those files, the data from those files, and we create our variables of red, green and blue. And we do some balancing between the different channels in order to optimize the combination for true color. We're basically using what's known as a tri-stimulus approach here. So we have different coefficients to help map the radiances we get from the sensor to a red, green and blue combination of channels. Here we do a little bit of work to stack the data together so that we can create the image. Here we then do some normalization in order to help us approximate the color in a way that we would understand for the human visual system. We also apply a histogram that helps to improve the image in terms of making it the combination between the different colors smooth and again realistic. And then we map the image that we have in terms of numbers onto a color array, which we can then use to actually create the image here. In this section of the code, we initialize the actual figure, the plot that we want to create, and we're going to use a function in here called pcolorMesh, which allows us to create a two-dimensional image based upon the data that we're providing from the RGB channels that we combined above. There's various things in here that go on to set the limits of the plot, add some grid lines, etc. And you can learn more about these in more detail. If you want to know in detail what all the different functions in Python do, the help online is really, really good. If you just search Python and then the name of the function, it will come up on Google and tell you most of what you need to know in order to implement these different parameters. If we then execute that code block there, we get a very nice image here of the Baltic Sea. And I'm sure you'll agree that this clearly does not look like, this is the ocean here and this is land, this clearly does not look like a normal patch of ocean. What we have here is a huge cyanobacterial bloom that we can see being moved around by the different physical features that are present in this area, such as currents that are creating eddies all around the land. So you can see here why a traditional chlorophyll algorithm designed for the open ocean might struggle with this level of activity and complexity. You could run this script in principle with almost any ULTI level 1 product, or in fact with other products that are providing optical data as well. It'd be easy to adapt this kind of approach for using with Sentinel-2 data. So I would recommend after you've done this, run it for this example. You could change the area that you're interested in and see what a true color image looks like of the ocean in a different area that you have an interest in.